You ever get that feeling that you're just looking at a problem from the wrong angle? Well, in math, sometimes all it takes is a change in your point of view, your entire coordinate system, to turn something that's impossibly complicated into something, well, kind of beautiful and simple. So today, let's explore how a simple change in perspective can unlock a whole new world of mathematical art. Okay, so take a look at this. It's a chambered nautilus, right? One of nature's most perfect spirals. And you see the shape everywhere, from galaxies way out in space to the seashells on the beach. But how would you actually write an equation for it? I mean, how could you tell a computer to draw this exact elegant curve? So, if you tried to use that standard, graph paper system we all learned in school, the good old Cartesian plane with its x and y axes, the equation would be an absolute nightmare. Seriously. It's just not the right language for this kind of shape. But don't worry, there is a much better way. And that better way, it involves a complete shift in our point of view. Let's take a look at what that new perspective is all about. Okay, the best way to wrap your head around this is with a simple analogy. Think about rectangular coordinates, our familiar x, y, like you're navigating a city grid, right? You go 3 blocks east, then 4 blocks north. It's all about that grid. But polar coordinates? They're more like using a compass. You just face a specific direction, say northeast, and then you walk for 5 miles. So it's a total shift from over and up to direction and distance. So if we're going to use this new compass system, we need to learn the language. Let's break down the basics, the r theta of it all. All right, in this polar world, we've got a few key terms. The center point, we don't call it the origin anymore, we call it the pole. That starting line, which is kind of like the positive x-axis, that's our polar axis. And to find any point, we just need 2 things. First is r, the radial coordinate. That's just the straight line distance from the pole. Easy enough. And second is theta, or theta, the angular coordinate, which is just the angle you turn from that polar axis. So here's the bottom line. Every single point on a plane can be described by just its distance from the center, r, and its angle, theta. That's it. Distance and angle, the whole shebang. Okay, this is all great, but you're probably wondering, how do we connect this new system back to the one we already know and love? Well, we need a way to translate between these 2 worlds. Let's build that bridge. And these formulas, they're basically our Rosetta Stone for translating. And honestly, if you remember a little bit of high school trig, SOHCAHTOA, TOA, you can see exactly where they come from. It's just a right triangle. The x-coordinate is the adjacent side, so that's where cosine comes in. The y-coordinate is the opposite side, so that uses sine. And these simple rules let us jump between the polar and rectangular worlds back and forth perfectly. Let's actually try one. Say we want to convert the rectangular point 1, 1. First, we find the distance r. We use our formula. R squared equals 1 squared plus 1 squared. So r is just the square root of 2. Okay, now for the angle theta. We know that the tangent of theta is y over x, which is just 1 over 1, or 1. So what's the angle whose tangent is 1? Well, that's pi over 4 radians, or, 45 degrees. So there you have it. The point 1, 1 in our city grid is just square root of 2, pi over 4 in our compass world. And hey, going the other way is just as easy. Let's take the polar point 3, comma pi over 3. To find x, we just do r times the cosine of the angle. So that's 3 times the cosine of pi over 3, which gives us 3 halves. To find y, we do r times the sine of the angle, which gives us 3 times the square root of 3 over 2. Simple as that. Now, here's where things get a little weird. It's a fun quirk of the polar system. See, unlike a city grid where every address is totally unique, a single point in the polar world can have, infinite different names. Just think about it for a second. Facing a certain angle is the exact same as facing that angle and then doing a full 360-degree spin, right? You end up in the same spot. So the point 2, pi over 3, is the exact same location as the point 2, 7 pi over 3. They land on the same dot. All right, so we've learned the grammar, we've learned the vocabulary. Now it is time for the really fun part, seeing the absolutely beautiful art these coordinates can create. Because if we think of coordinates as a language, then the equations are the poetry. And believe me, the poetry written in polar coordinates, it creates some of the most stunning, jaw-dropping curves in all of mathematics. So how do we actually do it?
Well, it's the same way we've always plotted graphs. We just make a table of values, we pick a bunch of different angles for theta, we plug them into our equation, and we see what distance r pops out. And as that angle, theta, sweeps around, r changes, and we just trace out the path.
And look what happens when we plot all those points from the equation r equals 4 sine theta. Boom, a perfect circle just emerges. Now, think about the equation for the same circle in rectangular coordinates. It'd be something like x squared plus y minus 2 squared equals 4. I mean, so much clunkier, right? The polar equation is just elegant. And listen, circles are just the beginning. There is an entire zoo of these beautiful polar curves. You've got things called limacons, which kind of look like dimpled hearts. There's a special type of limason called the cardioid, which is a perfect heart shape. And then there are my personal favorites, the rose curves, which, you guessed it, look exactly like flowers. And there's this amazing little trick for those rose curves. Just look at the number that's multiplying theta inside the cosine. We'll just call it n. Now get this. If n is an odd number, the flower will have exactly n petals. But if n is an even number, you get double that amount. You get 2n petals. How cool is that? And that brings us right back to where we started. Remember that impossibly complex spiral from the Nautilus shell? Well, in polar coordinates, its equation is beautifully, almost shockingly simple. It's what we call a logarithmic spiral. It's just a shape where the distance r grows exponentially as the angle theta increases. A really simple rule that generates this incredibly profound natural complexity. So, okay, these curves are obviously beautiful, but is this just math for math's sake? Is it just art, or does this new perspective actually matter out there in the real world? Oh, it absolutely matters. Polar coordinates are the natural language for anything that spins or rotates or repeats in a cycle. Think about the orbits of planets, right? Or how radio waves spread out, the spinning blades of a helicopter, the path a robot arm needs to take to grab something. In fields like physics, engineering, and computer graphics, this stuff isn't just a neat trick. It is an absolutely essential tool for describing the world we live in. It just goes to show you, sometimes the hardest part of solving a problem isn't doing the math, it's finding the right way to look at it in the first place. And that kind of leaves us with one final thought to chew on. What other complex problems out there, maybe even in your own life, might suddenly become simple if you could just find the right point of view?